In the vast and predictable machinery of our solar system, true precision is a rarity. But in early 2025, astronomers witnessed something that shook that sense of certainty. A massive interstellar object, 3I/ATLAS, received a faint, unexplained push as it passed near the Sun. A gentle nudge, yet powerful enough to alter its entire trajectory, steering it toward a point in space thousands of kilometers wide, aligned with almost impossible accuracy. A coincidence so improbable, its odds are roughly 1 in 26,000. This is the story of that object, and the quiet mystery it carries across the stars. As 3I/ATLAS moved closer to its perihelion, the moment of its nearest approach to the Sun, astronomers began noticing something they didn't expect. Across several observatories, from ground-based telescopes to deep space instruments, the data revealed a subtle but undeniable acceleration. It was too small to be visible in images, yet its signature in the orbital calculations was unmistakable. This was not gravity. It wasn't pressure from the solar wind. And it wasn't the kind of predictable outgassing we normally see when a comet warms and vents ice into space. NASA flagged the anomaly. Teams ran models, checked for errors, recalculated again and again. But nothing natural fit both the timing and the precise magnitude of the push. It appeared suddenly, then stopped just as abruptly. And before the scientific community could investigate further, 3I/ATLAS slipped behind the Sun, vanishing into the blinding solar glare. For weeks, the solar system's newest interstellar visitor became completely unobservable, leaving behind only questions, and a trajectory that no longer made sense. As 3I/ATLAS drew closer to its perihelion, its closest point to the Sun, astronomers expected the usual behavior seen in long-period comets: a brightening coma, predictable jets of vaporizing ice, and minor disturbances easily explained by solar heating. But what they observed instead was something far more unusual. Across multiple observatories, from high-precision ground telescopes to deep space monitoring instruments, the data began to show a subtle, unexpected drift. A slight acceleration, far too small to notice in real time, started nudging the object off its projected course. It wasn't dramatic, it wasn't visible, but in the orbital calculations, the signal was clear and consistent. Something was pushing 3I/ATLAS. And that push did not come from gravity. It wasn't caused by a passing body, a dust impact, or solar radiation pressure. Even more puzzling, the force didn't match the typical patterns of outgassing, the natural jetting of ice that explains most cometary thrust. Instead of a gradual buildup, the acceleration appeared suddenly, held its magnitude with remarkable steadiness, and then faded out just as quickly. NASA's trajectory analysts flagged the anomaly immediately. The readings were clean, the instruments functioning normally, and the signal appeared across independent datasets. Researchers from several institutions attempted to model the event, testing everything from uneven heating to exotic volatile compounds. But no natural explanation reproduced both the timing and the precision of the push. It was as though the object received a brief, calculated nudge, at exactly the moment when such a nudge would have the greatest effect on its long-term orbit. And then, just as the scientific community began focusing its attention on the anomaly, 3I/ATLAS moved into the Sun's glare. From Earth's perspective, it slipped behind the solar disk, becoming completely unobservable. Telescopes lost its signature. Tracking software stalled with blank fields. For the first time since its discovery, the interstellar visitor disappeared. For several long weeks, astronomers were left with nothing but partial data, unanswered questions, and a trajectory that no longer matched any natural expectation. The solar system's newest wanderer had gone dark, leaving behind only a faint, unexplained acceleration, and the growing suspicion that something extraordinary had just happened. When 3I/ATLAS finally emerged from behind the sun, astronomers wasted no time. Arrays around the world locked onto its faint signal, feeding fresh positional data into orbital models that had been frozen for weeks. What they discovered stunned them. The object was no longer traveling along the trajectory predicted before perihelion. Instead, its orbit had shifted, subtly at first glance, but with a precision that became more unsettling the deeper researchers looked. This was not the kind of random drift typically caused by uneven outgassing or numerical uncertainty. It was a clean, coherent adjustment, redirecting the interstellar visitor toward a very specific target: Jupiter's Hill Sphere. The Hill Sphere represents the invisible frontier where Jupiter's gravity begins to dominate over the Sun's. For a planet as massive as Jupiter, that boundary lies an astonishing 53 million kilometers from its surface. A gravitational territory so vast that entire swarms of asteroids, dust, and irregular moons reside within it. To reach that boundary by accident from interstellar space after a single unexplained acceleration near the Sun is statistically absurd. It would be like launching a spacecraft from Earth and having it graze the edge of a ring hovering above another continent. Without guidance, without correction, without intention. A level of precision that defies ordinary celestial mechanics. And yet, that is exactly where 3I/ATLAS is headed. Its path cuts toward the outermost edge of Jupiter's gravitational domain with astonishing accuracy. Not too shallow, not too steep, but aligned with a narrow window of space that even advanced space agencies would struggle to hit deliberately. To astronomers, this wasn't just unexpected, it was extraordinary. Because natural objects, influenced only by gravity and chaotic outgassing, do not normally execute precision maneuvers on the scale of tens of millions of kilometers. Something had nudged 3I/ATLAS onto this new trajectory. Something had done so at exactly the right moment. And now, as the object continues its silent approach, the question is no longer whether its path has changed, but how and why. The precision required for any object, natural or artificial, to reach Jupiter's Hill Sphere is nothing short of extraordinary. In celestial mechanics, even tiny deviations grow into massive divergences over millions of kilometers. Arrive too close to Jupiter, and the planet's immense gravity will hurl you away at breathtaking speed, flinging you out of the system like a stone from a sling. Arrive too far, and Jupiter's influence fades, leaving the object under the Sun's control, destined to drift past without incident. For 3I/ATLAS to intersect this boundary at exactly the observed distance and timing is an orbital bullseye of staggering accuracy. And all of it occurring after a single, brief, unexplained acceleration near the Sun. A push so small that most comets wouldn't register such a clean response. Harvard astrophysicist Avi Loeb examined the trajectory and described the situation as remarkable. Not because it violates physics, but because the numbers behind it strain the limits of natural probability. His calculations show that for random forces, outgassing, thermal jets, or gravitational perturbations, to produce this exact outcome, the odds drop below 0.004%. A fraction of a fraction, a statistical ghost wandering through the data, almost too small to take seriously, until now. Yet here it is, a real object, tens of billions of tons in mass, gliding through the solar system along a track that aligns with a gravitational boundary no natural process should target so precisely. It is like watching a drifting log in a river suddenly navigate toward a narrow channel miles downstream, hitting a gap that even a trained pilot would struggle to reach. Nature can do this, but only rarely, and almost never with such elegant precision. As 3I/ATLAS continues its journey, astronomers around the world are confronted with a quiet but profound question. How did an interstellar object, influenced by forces we barely After emerging from behind the Sun, 3I/ATLAS began to reveal more of its behavior, and one feature stood out immediately. Multiple jets of material were seen erupting from its surface, thin streams of vapor and dust tracing delicate arcs into space. For a comet, this is entirely normal. As sunlight warms buried ice, pockets of gas escape violently, creating natural thrust. But in the case of 3I/ATLAS, the pattern was unusual. The jets weren't random. Several of them pointed in directions that, when modeled, lined up almost perfectly with the course correction needed to place the object on its new trajectory. A trajectory that led straight toward the edge of Jupiter's Hill sphere. It wasn't enough evidence to suggest anything unnatural, nothing alarming or overtly engineered. Yet the alignment was precise enough and the timing clean enough to make researchers pause. Could these jets be natural? Absolutely. They fit comfortably within the physics of cometary activity, but could they also act as thrusters, producing small, deliberate adjustments? The physics is exactly the same. Gas pushing against vacuum. Momentum shifting ever so slightly. The only thing that changes is intent. And intent is the one variable nature doesn't usually supply. Loeb proposed a provocative idea, not as a declaration but as a question worth examining. If 3I/ATLAS were, in some distant possibility, an artificial probe, there would be no better moment to adjust its course than during perihelion. The Sun's immense gravity functions like a cosmic slingshot. A tiny push at the right moment can translate into enormous orbital changes millions of kilometers later. In that context, the unexplained acceleration recorded near the Sun becomes more than a curiosity. It becomes a perfectly timed maneuver. And if a probe intended to deploy smaller instruments into Jupiter's gravitational domain, the Hill sphere would serve as the ideal insertion point. At that boundary, Jupiter's escape velocity drops to just 2.2 kilometers per second, low enough that a small released object could settle into orbit with only minimal propulsion, letting Jupiter's gravity handle the rest. A simple, efficient, almost elegant strategy, if such intention existed at all. Course correction needed to place the object on its new trajectory, a trajectory that led straight toward the edge of Jupiter's Hill sphere. It wasn't enough evidence to suggest anything unnatural, nothing alarming or overtly engineered, yet the alignment was precise enough and the timing clean enough to make researchers pause. Could these jets be natural? Absolutely. They fit comfortably within the physics of cometary activity. But could they also act as thrusters, producing small, deliberate adjustments? The physics is exactly the same. Gas pushing against vacuum. Momentum shifting ever so slightly. The only thing that changes is intent. And intent is the one variable nature doesn't usually supply. In the grand architecture of the solar system, Jupiter stands as an unmistakable titan. It is the largest planet we have, a massive gravitational anchor shaping the orbits of countless bodies around it. Its swirling storms, colossal atmosphere, and powerful magnetic field can be detected from extraordinary distances, a planetary lighthouse in the dark. If a distant civilization were scanning nearby star systems for signs of structure or stability, Jupiter would be the first feature they'd notice. Not Earth, small and faint beside the Sun, but Jupiter, bright, dominant, impossible to overlook. In that sense, it becomes the perfect marker, a signpost pointing toward the smaller terrestrial worlds that orbit closer in. If someone, or something, were navigating the solar system, Jupiter is the planet they would see long before they ever noticed us. NASA remains cautious. Despite the growing list of unusual behaviors, every anomaly observed so far is still classified as natural until evidence proves otherwise. This caution isn't skepticism, it's discipline. Decades of studying comets and interstellar debris have shown that nature can be far more inventive than we expect. Recent images captured by the Mars Reconnaissance Orbiter reveal no obvious signs of artificial structure on 3 Pasi/ATLAS. No clean edges, no repeating geometry, no signatures that would immediately suggest engineering. To NASA, that absence matters, and yet scientists acknowledge a critical truth. Objects from beyond the solar system may contain volatile materials we have never encountered, chemistries that respond to solar heating in unfamiliar ways. Jets, bursts, even abrupt accelerations could arise from processes still outside our models. For now, the agency's official position remains conservative and consistent. 3 I/ATLAS is a comet, an unusually large, unusually precise, unusually active comet, but a comet nonetheless. On March 16, 2026, 3 I/ATLAS will skim the outer edge of Jupiter's Hill sphere, the precise boundary where the giant planet's gravity overtakes the sun's. Across the globe, major observatories are preparing for that moment. Hubble, ground-based arrays, and even the Juno spacecraft are adjusting observation plans to capture every possible detail. If the object accelerates again, if it alters its heading, splits apart, or releases smaller bodies, the world's instruments will catch it in real time. Whatever happens at that boundary, natural or not, will reshape our understanding of this visitor, and perhaps our understanding of interstellar objects themselves. At this moment, 3 I/ATLAS drifts through the solar system as an unsolved mystery. It may be a rare natural object, following rare natural rules, or it may challenge everything we think we know about interstellar visitors. As it nears Jupiter, one question hangs over the scientific world. Is this the most improbable comet ever observed? Or the first hint of something designed? For now, the answer waits quietly among the stars,